Okay. So I'll upload this in your course page. This particular program. So what it does is, okay. What I will do, I will just share my desktop. Okay, and then explain about this. So yeah, this was the path to my particular one of my particular laptops. So you have to modify this to your path to your data set. Okay, so let me just share my desktop and then explain this and then run the program and see what happens. Okay, so share my desktop. So all of you are able to see. So are you able to see my desktop? The screen, the program is visible on the idle editor. Okay. So let me just increase the font size a bit. So in this again, the count vectorizer is something that we have seen earlier. Okay, so we are importing that because we want to create tokenize all of the words. Okay, we'll use pandas. Okay, to create two columns in the table. One is for labels. Okay, so first of all, what is the data set? So have you seen the data set? How many of you have seen the data set? Anyway, so even if you have not seen, let me just open that file. So this is how the data set looks like. So you can see that it is the first. It has multiple lines. So in each line or in example or each document consists of two parts. Okay, the first word in every document is the class, whether it is ham or spam. Okay, so this first one is, for example, ham. Okay, and then next will be somewhere down. You'll see that the next one will be spam. It is not showing correctly, so let's open it. Something else. What pad? Yeah. So here you can see that the first one is ham, then second is also ham, third is spam, fourth is ham, and so on. Okay, so the first word is the class, the label. Then there's a tab, character, and then the SMS message. Okay, so it has only two parts, class and SMS messages, and they are separated by tabs. So that's why when you read this table using pd.read table, you will tell the separator is tab. Okay, you are telling that the separator is tab character. Okay, name of the data set. This is the path to the data set and the name of the file. And there is no header. Okay, there is no name of the columns. So header is good, none. And then what names you want to give to each of the columns on the in the table. So because they don't have any names, so here you want to give first one is label, right? And then the second one is the message. Okay, so I'm just calling it MSG for the second column, and the first column is I'm calling label in that order. Okay, so names I want to give it, give the data frame columns name as label and message. So label will contain all the labels for the different examples, and the message will be the actual message. So df label will be the label, df message will be message, SMS message. Okay. And one more thing we are doing just before going further is we are just converting them into numbers, binary variables 1 and 0. Okay, So spam is given value of 1 because that is what we are looking forward, right? Otherwise, most of the mails are non-spams, but some of them are spams. So we are giving one value to spam because we want to find out the spam mails. That is the important ones. And ham we are giving value of 0. Okay, so this line, this particular line, df.label.map, it is just mapping wherever you have a spam in the label is giving it value of 1, and wherever it is ham, it is giving value of 0. So now after that, instead of ham and spam, you'll get df of label as 1 or 0. Okay, so maybe we can just look at it. Print df label. Let's look at the first 5 labels. Let's not worry about the remaining part. So I'm just commenting it out. I'll just later on remove the comments. Okay, I just want to see the first 5 examples. Okay. Right. So you can see the first 5 labels are 00100. Okay, that is spam spam, ham spam spam, or ham ham spam ham ham. Okay, yeah, ham ham spam ham ham. Okay, because ham is 0, spam is 1. Okay. Ham is 0, spam is 1. Okay. Does it work? Okay, so we want to look at the complete table, first 5 rows of the complete table. You can just go like this. So you can see now the label and the message as well. Okay, so the first 2 are ham, third one is spam, looks like spam. Okay, free entry and all these things. Alright, so let's move this here. And before this, before you perform this mapping, if you just type, just copy this. Before the mapping, you'll see that instead of 10, it would be ham and spam, right? Ham ham spam, ham ham. So before you perform the mapping, it was like ham ham spam ham ham. After the mapping, it is 00100. Okay. So because that is 1 and 0s are internally used. So later on, when you perform classification, the 1 and 0 is what you should give the values, not ham and spam. Those are not understood many times. Okay, now let's remove these things and comments and proceed further. Then now we are calling count vectorizer, which will again create tokens. Each word will be separated as a token. Stop words will be removed by default. Okay, and punctuation marks will be removed, and so on. So everything is done, and then you will call this fit transform to the df message. So this column, this message column, or each of the example in each of the document. Okay, we didn't see how many documents are present, so maybe you can just have one more line. So print df. What is the code for the disk type? Or save maybe, yeah. So df.disk type tells that there are a total of 5572 examples. Okay, so there are 5572 total number of examples. Okay, including spam and ham documents. Okay, so there are total more than 5,500 total number of SMS messages, more than that. Okay, so now you created count vectorizer and you just call fit underscore transform. So this will create the vocabulary and then transform each of the documents according to that vocabulary. So we'll just count each of the frequency of each of the words in the vocabulary. of the vocabulary. And then this train test split, we have already seen this earlier. So we want to create a split of, let's say, 30% of test size. So we want out of 5,500 something, we want to create 70% training documents, 30% test documents. Okay, so we want to just test on 30%, train on 70%. So it will create that split. So X train, Y train will be the messages and the labels in the training set. X test, Y test will be the messages and the labels in the test set. So X is our tokenized examples, okay, and DF label is their corresponding labels. Right? Each of the example will have labels. So DF label gives that those labels 1100 like this. And then random state. Okay, we also want to create exact same split every time we perform the experiment, so that it's reproducible. So random state we are setting it as 42. Okay, it's my habit to just set it to 42. You can also use some other number if you want. Okay. If you don't use random state equal to 42, then you'll see that for different runs, a different set of training and test will be created. Okay, different. So it will be 70-30. It will be a stratified one, but the actual documents in the training set and testing set will vary, will differ from run to run. From each of when you run each time, you'll see a different example. If you use this random state equal to 42, then it will seed the example in such a way that you always get the exact same training set and test set. Okay, now next one is the multinomial naive Bayes. So this is the name of the naive Bayes classifier in scikit-learn. Okay, so you can see that we have included it here. So actually there are multiple kind of naive Bayes classifier. There are also something called Bernoulli naive Bayes, in which case that is used when each of the feature can be is a binary variable. Okay, so here in our case, the features are counts, right? Each of the words count. So this is not binary. In some cases, when it is binary, then you use Bernoulli naive Bayes. So that is not important here. So multinomial naive Bayes means each of the feature can have any value, any integer value. So multinomial naive Bayes. So CLF is our classifier, and then we are fitting it on X train, Y train. We are now creating the model. We create the model. So creating model in case of naive Bayes means it will just learn the probabilities of each of the word being present given a document, a label. Okay, so what is the probability of this given this label? Probability of this given this label. It will create those kind of probabilities to be used in a naive Bayes formula. So this will create the model CLF.fit. Once you have created the model, now you want to predict on something. Okay, and you have already created a test split. So you want to predict on that. Okay, so this predict will CLF.predict will predict the label of each of the test example in the X underscore test set. Okay. And then I have also included metrics here, so which will be used to find the various accuracy and other scores based upon what are the predictions and what is the actual value. Okay, so in this particular case, let us say we want to find out accuracy score first. So accuracy, it will take first what is the actual value, array of actual values, and array of the predicted values. Okay. So the predicted values I have stored in pred short for prediction, or predicted variables, or predicted classes in the test set. Okay. So that is the second array here given. The first array is the Y test, Y underscore test. Remember in the split case, Y underscore test. Okay, when I highlight a test, is it visible to you also? So if, for example, I have highlighted Y underscore test, so is it visible to you? Yes or no? Okay, okay. So that is fine, right? So y underscore test is the label ordered in the, of the label ordered label of the test set. Okay. So X test are the examples and corresponding labels are in Y test. Okay. So actual labels, that is Y test, and the predicted labels will be compared, and depending upon that what is the accuracy will be printed by this result, matrix dot accuracy score. Okay. You can also print a confusion matrix that I have again imported here from sklearn dot matrix. Okay, maybe it is not required because we've already imported matrix, so maybe it is not required. So we can directly use matrix here. Okay, matrix dot confusion matrix. Okay, so now let's now try to see the output of this. Okay, so now it is run, finished. Let us remove the clutter. Let's run again. Okay, so this is the accuracy. You can see that accuracy is very high, 98%. And this is the second matrix that is given is the confusion matrix. Okay, so here, so the first column is the actual ham messages. Okay, what is the number of ham messages and how many of them were actually predicted to be ham. So you can see that 1432 have been correctly predicted as ham messages. Okay, and similarly, the diagonally, the second one is the test set of it is the number of spam messages in the test set. So they are total of 215 correctly labeled spam messages. Okay. So let us now try to find out whether the column here, that is second column 16, first row second column 16, whether this is the incorrectly labeled ham, number of ham messages or spam messages. So we can find it out actually. So before that, let's look at, let's print the maybe precision. Okay, so we can also print precision score. Once you print this, you'll easily get your answer. So precision score is 93. So let us see, 215 divided by 231, 231.0. 9307, yeah. So that is the same answer, the first as first. So that means the precision is the same as this thing, and the sum of these two is 231 that we have found. So that means this is the predicted column are the predicted values, and the rows are the actual values. Okay. So the first row here is the actual ham messages. Second row is the actual spam messages, and the column wise they are predicted spams and predicted hams and predicted spams. First column is prediction of ham. Second column is predicted spams. Okay. So if you want to find, say, let's say now, what is the recall? Okay, given this is the contingency table, what will be the recall? Again, 215 is the predicted spams. Out of how many total spams are there? 215 plus 9, right? Because the rows are the actual ham or spam, and you can see that second row is spams, smaller number of spams. So 215 plus 9 is 224. So you can see that the recall is 0.959 something, and you can actually see the recall score, when you look at the recall score here, see they'll get the same answer as this thing. Okay, yeah, you can see that we got the answer same as what you have calculated earlier. So recall is 0.9598. Okay. And what formula you think was used to get the accuracy score here? What is the formula for accuracy? Accuracy came out to be 0.98 something, right? Earlier. Yeah, 0.9854. So what is the formula for accuracy? Accuracy just means out of all the samples, how many were correctly labeled as either positive or negative. So here positive is spam, negative is ham. Yeah, so diagonal elements, that is true positive plus true negative by n. Yeah, that is correct, Vivek. Okay, so diagonal element here of 1432 plus 215 and divide by total. That means you will also add 16 plus 9, 25. So yes, so we get the value as 0.985047 all this. Okay, but as we have explained earlier, because here you have a very large number of ham messages, okay, which may be easier to predict. So you will get a good result anyway. Right? Even if you predict everything as let's say ham, you still get a good result. Okay, so what score should you use now? F1 score. Okay, let's try to use F1 score instead of that. F1 score. So that value will be smaller than the accuracy value. So you can see now the F1 score is 0.94. It's smaller than the 0.98 accuracy value, but still it's quite high. Okay, so the naive based classifier is actually working pretty well in this case. Okay, and in fact the one of the first, the junk classifier, spam classifier, email spam classifier, was built using the same method. Okay, it was very rudimentary, but still it gave a quite good result. Any doubts so far? Is it clear? One more thing, I've explained about that Laplace smoothing, +1 smoothing. So in multinomial naive Bayes, this when you are calling this function, that is by default that +1 smoothing is applied here. Okay, you can actually you can see here the alpha is equal to 1 is their default by default. Okay, and this one actually means additive Laplace smoothing. You can see here in the scikit-learn that API's documentation, they play written that default it is +1 smoothing is used, right? So if you don't want to give here, so what is the name of that? Default. Okay, so default you may give value of 0 and see what happens now. So you don't want to do add one smoothing. It will give some warning, but it still gives very small value and continue. You'll see. Oh, default is not there. Sorry, alpha, not default. Okay. Right. So now you can see that without Laplace smoothing, your F1 score has actually gone down 0.928. Earlier it was 0.945. Okay. So Laplace smoothing always by default it's performed so that those 0 probabilities can be removed. Okay. It is never, the probability does never become 0. Okay, so even if you give 0 value of alpha, you'll see that it will not take 0, it will take some small percentage. So you can see here the warning is coming like this. When you give 0 alpha value as 0, it's saying that alpha too small will result in numeric errors. That means the probabilities will not be calculated properly. So setting to a very small number, that is 1 to the power -10. Okay, 0.00009 times and 1. Still not is not making it 0. Okay, some small, very small smoothing is still performed. Okay, it's always done. Okay, so I will just stop sharing. We'll come back to this after some time, or in a short while when we continue with the next. Okay, let's look at what happens when you perform the decision tree. Okay, you can take it as homework. Okay, let I will give it as homework to you. So on the same data set, instead of the multinomial naive Bayes classifier, just try to use decision tree classifier and see what is the answer. Okay, and look at the documentation of decision tree online and try to set some of the parameters. Okay, there are a lot of parameters to be tuned in case of decision tree. Okay, and you'll see that the result that you get in decision tree will not be as good as what you get using naive Bayes. Okay, so this is one of the examples, one of the few cases where the naive Bayes actually beats decision tree. So it's a very positive case for naive Bayes classifier. Okay, most of the time, other times you'll see that decision tree might give better results, but it is one of the times when naive Bayes actually outperforms decision tree and many other classifiers. Okay, so let's look at some of the more classifiers. We'll not go into detail about those classifiers, but we'll just see in the same example how we can, instead of calling multinomial naive Bayes, how we can call those classifiers in the same example. Okay, so the first one is the support vector machine. So it's one of the most popular and one of the strongest classifier. Okay, and many times this is the classifier that performs the best. Okay, and it's one of the top classifiers, so support vector machine. But thing is that the mathematics behind it is a bit complex, so I will not go into that. Okay, but I'll just explain what it does. Okay. So let's say there are two classes. So there's one class in this diagram which is drawn as squares, blue squares, and the other class is drawn as red squares. Okay, they are in there. There are some examples, some samples which are just there in 2D. It's just shown in 2D, but they may be in 3D, 4D, some other dimension. Okay, so the idea behind the support vector machine is to find a boundary. Okay, so a boundary, or you want to say you want to separate these blue squares from red circles, or separate these two different examples which belong to different classes by using a boundary. Okay, such that the margin becomes maximum, or you want to maximize the margin. Okay, or you can say you want to create a boundary such that from the boundary, relative to the boundary, the distance of the two classes, okay, is maximized. Okay, it's just simple. It's just simple. I'm being too simplistic, but that is the idea. Okay, you just want to maximize. You just want to create a boundary that maximizes the separation. Okay, so the idea here is to find some vectors or some examples which are called support vectors. So why it's called support vectors? Because certain examples are taken. So this what it does. What this classifier does is, it, after all the mathematics, all the computations, it selects some of the examples from both classes as support vectors. Okay, and then it creates a boundary with respect to those support vectors. Now after that, after it has created those support vectors, after all the calculations, okay, there's now other examples, other samples apart from the support vectors now don't matter. The only support vectors are what will be used to calculate the margin from the boundary. Okay, so you want to maximize the margin, or you want to maximize the margin between the two support vectors. So the boundary you want to create is boundary that will maximize the margin. Okay. and it can be the boundary cannot is not necessary that you always create a linear line like this. The boundary can be any shape you want. Okay, any shape that maximizes the margin. Boundary can be of any shape. But here for simplicity, and especially when you are using text, okay, the linear kernel as it's called is used. Okay, that is like a bound, like a straight line. Okay, so here in 2D dimension it looks like a straight line. So let's continue with that. I mean, assuming that we are using linear kernel, so it's a straight line. Okay, so this margin is maximized. You are creating that boundary in such a way that this margin is maximized. Okay, so many times you'll see that maximum margin classifier is used for support vector machine, maximum margin. Okay, so after all the calculation and the model creation in support vector machine, whenever the model is created, ultimately what it is trying to do is it's trying to find those support vectors which will maximize the gap between the support vectors of the two different classes. Okay, so why is that so? What is the benefit of maximizing this, or finding that boundary which maximizes this difference? Any idea? What will be the benefit of maximizing or finding that boundary which maximizes the gap between positive and negative? Because it helps in classification. In what way? Let's say you want to separate, or you want to classify a new document, right, or in a test set. So what will help? How will it help if you have a big margin? As opposed to when you have a small margin. Okay, so having a big margin, or having found that boundary which maximizes this, will make sure that on one side of it, the probability of examples falling one side of it, okay, and that belonging to that particular class will be much more. Okay, so in this case, if the boundary is properly set, and if you get a new example, okay, new label, so the probability that it will fall into this particular red range, okay, will be much higher if it is actually red circle. Okay, and similarly, the probability that it will fall into this blue region and actually that it is blue will be much more. Okay, so that margin helps in that. So let us look at how you will actually be using this in the program. So let me again share the desktop and see what happens. So I've already explained that it is a very strong classifier. So we expect to get better results than naive Bayes, because most of the time support vector machine, it beats naive Bayes. Okay, naive Bayes is a very basic classifier, and it's used as a baseline, okay, as the ground, as the baseline that you have to beat in most of the research area. Okay, so naive Bayes is a very basic classifier, and support vector machine is a very strong one. So it is expected to beat naive Bayes most of the time. Okay, unless the data is such that naive Bayes is getting advantage due to some reason. Okay, so let us. So I'm sharing my desktop again. So let us now again do the same thing, but instead of this multi-domain no Bayes, let's now actually call SVM so in scikit-learn, it's SVC, support vector classifier. Okay, it is the same support vector machine classifier. It's called support vector classifier. So there's not much difference here, except that the calling instead of multi-nominal naive Bayes, you'll call SVC. Okay, and kernel, as I explained, you'll use linear kernel because that's what works the best. Other kernels will not give you the desired results, and also you want reproducible results, and it requires certain random number setting. So that's all. You can see that how easy it is. You can use any classifier you want, just import that classifier and fit it here, and you are done. Nothing else. Hopefully, if you have imported correctly, you'll get the result. Okay, now you can see that you've got the result, and the F1 score you have got is 0.9557. Okay, so it is much better than the 0.9282. It's better than the naive base. Okay. And especially the precision here is very high, right? The precision you got is 1. It didn't label any non-spam as spam. Okay, only spam was labeled as spam, but that it did at the cost of labeling or missing out something. The recall was less. Okay, it missed out on some of the spam classifiers which went to the non-spam class. So it didn't label some of the spam as spam. It labeled some of the actual spam messages as non-spam messages. So 19 of them it did. Okay, so it also has certain settings. So one is like C value. So maybe you can increase this. So by default it is 1. So this parameter you can actually use. Okay, so you can see that by using this slightly more improved result are obtained. Let's try to increase further. Let's see what happens. Okay, so at 10 you get the best result. Let's see value of 10. Okay. Or even without that you are getting quite better results. So you can continue using this. Default value of 1. Okay, so one more classifier before we stop is called KNN classifier. So we'll just again look at that. Okay, so the KN classifier. So I'll just show it in the desktop itself. So what happens in the KNN classifier is, you can see the slide, right? So in KNN classifier, what you do is look at each example, okay, and its K neighbor. So K has to be, so K is a parameter that you have to find out. K is a parameter that has to be found out based upon the data set. Okay, so K, maybe you look at starting with K is equal to 1, then maybe K is equal to 2, 3, 4 like this, or K is equal to 1, 3, 5 like this. Okay, and then for each example, let's say we have set to K is equal to 3. Let us say, for example. Okay, so for each example, you look at the K nearest examples. Okay, K examples which are nearest to the example that you are considering. So let us say we are considering this particular example, that is the red star inside the circle. Okay, so if K is equal to 3, it will look at the 3, or here let's say the example is question mark. Okay, the question mark is what you want to find out. So to find out what is the label of that, you look at the nearest 3 examples, which are the 3 examples which are nearest to that. Nearest means according to some distance, right? Whether it is distance based upon cosine, whether it is based upon the Euclidean distance, whatever distance measure you are using, you look at the distance of each of the other examples, and you'll find out the 3 nearest neighbors. Okay, so it is called K nearest neighbor. So here K is equal to 3. Okay, and then you'll see what are the labels of those. Okay, and the majority label, whatever the label has the majority, you'll set the label of this question mark as that. Okay, so in this particular case, you can see the inner circle, inner dashed circle. For the question mark, the 3 examples, the 3 so 3 examples, 3 nearest neighbors are 1 star and 2 greens triangles. So majority is green, so it will say it is green. Okay, now you'll ask, now this has to be done during testing time, right? So what is the purpose of training now? What is the purpose of training here? In naive based classifier, you learned about the probabilities. In In SBM, you learned about the margin, right? The boundary. But what is the training area? You can do it directly in the test set, right? So look at the three nearest examples. Find out the three nearest examples, and look at their majority label. So what do you think is done during training set or during the training phase in KNN classifier? Okay, so in during training phase, the nearest neighbors are found for each of them. Okay, so that nearest neighbor distances and all are calculated for each. Okay, so let's look at okay. No, it is not clustering. It is classification. Remember, here you have classified it as green. So let us look at how you can actually use this in neighbors. I think import k neighbors. Okay, hopefully I'm calling the name correct. If I'm calling the name correct, then it should be the correct result. K neighbors classifier. You have to set the value of n neighbors, I think. Otherwise, we'll check. Okay, let's say n neighbors equal 3. I will look at the API and okay, no, random state is not used here. No use of random state here. So we got the answer here. Okay, so k neighbors classified with n neighbors equal to 3 have got a very poor result as compared to the naive base and the SBM. It's only 0.65 accuracy. Okay, but in practice, for many cases, research, the k neighbors, k nearest neighbors classifier has found out to be giving good results. Okay, so here n neighbors equal to 1. Look at only one neighbor, the result is slightly improved. Okay, but it's still not as good as the earlier examples. Okay, so you can see that for spam, it is not able to classify properly. Okay, for hams it is fine, but for spams it is not as good. So it is basically labeling most of them as hams. Okay. So as a result, the recall of ham is quite good, but recall of your actual positive number, that is spam, is very less. Okay, recall will be, so it is classifying only a few of them as spam, only when it's very sure. So you can see that the precision is very high, 146 by 147, but the recall is very less, that is 146 by 146 plus 78. Okay, so recall is very less. So because of that, the F1 score has dropped down. All right, so we will stop here, and you can try setting some more. Just look at the APIs and try to set some parameters. They have a lot of parameters to be set, and see whether you can improve the result further. Okay, so I'll stop sharing the desktop, and if you have any questions, you can ask. If you run again and again, we get same result. Yes, you get the same result here. If you run again and again, yes. So you have learned about a naive base, decision tree, SVM, KNN, 4 classifiers are done, and logistic regression based classifier also I think we have done once, right? So 5 classifiers we have already done. So maybe we'll start with the clustering in the next session. Okay. So C value is something that is used to tune it, so don't worry about that. Okay, it's a more mathematical stuff. Okay, so don't worry about C values and what are the other parameters. but some other parameters are easy to understand. So just set those parameters in decision tree and KNN and other stuff. Okay. Quiz I will upload by maybe by Monday. Okay, maybe during Sunday also, and you'll get 10 days for that. And after that, we'll also have to do assignments. Okay, I'll also upload an assignment once we are done with class. Now we have done with classifiers, so I'll float some assignments also. Yes, there's no class tomorrow, I think.